Imagine you're holding something simple in your hand, a coin, a pen, anything at all. You let it go, and without hesitation it falls. No debate, no delay, no mystery, just straight down, as if the universe itself made a decision long before you did. You've seen it happen 1,000 times, so many times that your mind has stopped questioning it. Gravity, you say, and the story feels complete. But what if that answer is just the beginning of a much deeper question? What if I told you that nothing is actually pulling that object down? No invisible rope, no hidden force reaching out of the earth. Nothing grabbing it, dragging it, or commanding it to fall. And yet, it falls anyway. Not because it's being forced to, but because it has no choice but to follow a path written into the very fabric of reality itself. Now pause for a second and really think about that, because if this is true, then every step you take, every time you jump, every drop of rain, every orbit of the moon, none of it is what it seems. The ground beneath your feet isn't just holding you up. It might actually be stopping you from doing what the universe naturally wants you to do. This isn't just a new explanation of gravity. It's a completely different way of seeing the world. One that turns your everyday experience upside down. The familiar becomes strange. The obvious becomes questionable. And the deeper you go, the more reality begins to feel less like a set of rules, and more like a hidden story waiting to be uncovered. So don't just listen to this as another explanation. Treat it like an experiment. Keep your curiosity switched on. Keep your curious assumption. Challenge every assumption you've ever had about falling, weight, and motion. Because by the time we reach the end of this journey, you won't just understand gravity differently. You'll never look at something falling the same way again. If you drop a ball, it falls. If you jump, you come back down. It feels so obvious that something must be pulling everything toward the earth, like an invisible hand reaching out and dragging objects downward. That picture is simple, comforting, and, if we're being honest, not quite right. The real story begins when you start asking a slightly uncomfortable question. What does pulling even mean when there's nothing there doing the pulling? You can see a rope pull, you can feel your muscles pull, but gravity doesn't seem to have anything you can grab onto. For a long time, people were satisfied with saying it's just a force acting at a distance. But that idea always carried a kind of mystery with it, like a trick you accept without understanding how it's done. Then along comes Albert Einstein, who looked at this familiar falling ball and decided that maybe the question itself was wrong. Instead of asking what force is pulling the ball, he asked what the ball is actually doing. And this shift changes everything. Imagine you're floating in empty space, far away from any planet. If you let go of an object, it just drifts along beside you. No force, no pull, just motion. Now imagine that same situation near the Earth where the object starts moving toward the ground. The old way of thinking says there must be a force acting. But Einstein noticed something strange. If you were falling alongside that object, you wouldn't feel any force at all. Both of you would seem to float together, as if gravity had disappeared. That's a very peculiar kind of force, one that vanishes the moment you stop resisting it. So, instead of treating gravity like an ordinary push or pull, the idea becomes that something deeper is happening to space and time themselves. Not space as an empty stage where events happen, but space as something flexible, something that can bend, stretch, and curve. When you put a massive object like the Earth into this space-time, it doesn't just sit there quietly, it changes the geometry around it. It's like placing a heavy ball on a stretched rubber sheet. The sheet dips, curves, and any smaller object placed nearby will move along that curved surface, not because it's being pulled directly by the heavy ball, but because the surface it's moving on is no longer flat. Now, this rubber sheet picture is only an analogy, and like all analogies, it's imperfect. Real space-time isn't a two-dimensional surface you can look at from the outside. It's the very structure of reality itself, including time. But the key idea survives. Mass tells space-time how to curve, and curved space-time tells objects how to move. The Earth isn't reaching out and grabbing the ball. It's shaping the arena in which the ball moves. And the ball, simply by existing and moving, follows the natural paths available in that curved geometry. Here's where things get even more interesting. When an object is falling freely, like a skydiver before opening a parachute, it's not being yanked downward in the usual sense. In fact, from its own perspective, it's doing the simplest thing possible, moving in a straight line, but straight doesn't mean what you think it means. In curved spacetime, the straightest possible path isn't what looks straight to your eyes. It's what physicists call a geodesic, the path that requires no force, no effort, no deviation. The falling object is following this path naturally, like a marble rolling along a curved track without friction. It's not trying to go down, it's simply following the shape of the track. This leads to a surprising reversal of intuition. The object sitting on the ground, which seems at rest, is actually the one being forced out of its natural motion. The ground is pushing up on it, preventing it from following its geodesic path through spacetime. That push is what you feel as weight. If the ground suddenly disappeared, you wouldn't feel a force pulling you down. You would feel the absence of that force. You would be in free fall, weightless, even as you accelerate toward the Earth. Astronauts orbiting the planet experience exactly this. They are constantly falling, but they never hit the ground because their path curves around the Earth at the same rate the Earth curves away beneath them. Think about that for a moment. Weight, which feels so fundamental, so direct, is actually a sign that something is interfering with your natural motion. You feel heavy not because gravity is pulling you, but because the ground is stopping you from moving the way space-time wants you to move. It's an upside-down way of thinking about the world, where the absence of force corresponds to motion, and the presence of force corresponds to being held in place. Now consider light, which has no mass at all. If gravity were just a force that acts on mass, light shouldn't be affected by it. But observations show that light bends when it passes near massive objects. Stars appear slightly shifted in position when their light passes close to the sun, an effect that was famously confirmed during a solar eclipse and became one of the earliest triumphs of Einstein's theory. How can something without mass be pulled? The answer is that it isn't being pulled. Light always follows the straightest possible path available to it, but in a curved spacetime, those paths themselves are curved, so the light appears to bend, not because it's experiencing a force, but because the geometry it's moving through is not flat. This idea stretches your intuition in uncomfortable ways because it replaces a familiar concept, a force acting across space, with a more abstract one, the shape of space-time itself. It's tempting to keep asking, yes, but what is really pulling things down? And the answer keeps slipping away, because there isn't a thing doing the pulling. The motion arises from the structure of reality, not from an interaction in the usual sense. It's like asking what force makes a straight line the shortest distance between 2 points. There isn't one? It's a property of the geometry. And yet, from our everyday perspective, it still feels like a pull. When you drop something, it accelerates toward the ground. When you lift something, you have to exert effort against that motion. The language of forces works extremely well for describing these experiences, and for many practical purposes, it's perfectly fine to say that gravity pulls things down. But underneath that description is a deeper layer, where the pull is revealed as a kind of illusion, a convenient way of talking about motion in a curved space-time. This doesn't make gravity less real. If anything, it makes it more profound. Instead of being just another force among many, it becomes a feature of the stage on which all forces act. It's woven into the fabric of existence, inseparable from the way distances and durations are defined. When you measure how far something falls or how long it takes, you're already dealing with space-time, and gravity is already part of that measurement. If you keep pushing this idea, it leads to even stranger consequences. Massive objects can perp time itself, causing clocks to tick at different rates depending on how close they are to a source of gravity. This isn't science fiction. It's been measured with precise instruments and must be accounted for in technologies like GPS. The satellites orbiting the Earth experience slightly different time than clocks on the ground, and without correcting for this effect, navigation systems would quickly become inaccurate. So the same curvature that guides falling apples also shapes the flow of time, linking motion and duration in a way that defies everyday intuition. At some point, you might wonder whether we've just replaced one mystery with another. Instead of asking what pulls things down, we're now asking what causes space-time to curve and why objects follow geodesics in the first place. These are deeper questions, and physics continues to explore them, especially when trying to reconcile gravity with quantum mechanics. But even without complete answers, the shift in perspective is powerful. It shows that the way we describe the world can change dramatically when we look at familiar phenomena from a new angle. So when you see something fall, you can still think of it as being pulled downward, and that will serve you well in most situations. But you can also choose to see it differently, as an object moving freely through a curved space-time, following the simplest path available to it, while the ground beneath it resists that motion and gives rise to the sensation of weight. The same event, two descriptions, one deeper than the other. And somewhere in that difference lies the real story of what pulls things down. Not a hidden force reaching out from the earth, but the quiet, pervasive curvature of the universe itself, shaping every motion in ways that are invisible until you learn how to look. As we come to the end of this journey, the question we started with. What really pulls things down doesn't feel as simple as it once did. What looked like an obvious answer has unfolded into something far deeper and far more beautiful. The falling object, the weight you feel, the motion of planets, none of it is driven by an invisible hand pulling from a distance. Instead, it's the quiet shaping of space and time itself, guiding everything along paths that feel inevitable once you begin to see them. And maybe that's the most powerful idea to take with you. Not just about gravity, but about understanding the world. The universe often hides its truth behind what feels familiar. The things we think we understand best are sometimes the ones we've questioned the least. But the moment you dare to look again, to ask why instead of just accepting what, reality opens up in ways that are both humbling and inspiring. So the next time you drop something and watch it fall, don't just see an object moving downward. See a story unfolding, a story written into the fabric of the universe, where motion isn't forced but guided, where what feels like a pull is really a path, and where even the simplest moment holds a piece of something incredibly profound. Keep questioning, keep wondering, because the beauty of science isn't just in the answers. It's in the curiosity that drives you to look deeper. Good luck on your journey of discovery, wherever it takes you, and thank you for being here, for thinking, for questioning, and for exploring this hidden side of reality.